So today we're going to look at the probability when we have two or more events going on. So first, if we happen to have independent events, which means the probability of one of them occurring does not affect the probability of another one. So an example we've seen is tossing a coin. If you toss a coin twice, then the second flip does not depend on the first. And because sometimes these definitions make more sense when we have a non-example, we can consider having three names in a hat. Here, if we pick a name out of the hat, which name we choose certainly affects the probability that we choose a name second. So if we have Ollie, Brandy, and Cruz, their names are in a hat, and we're looking at the probability of pulling Brandy second, well, that depends on whether we pulled Brandy first or not. So if we already took Brandy's name out of the hat, then there is a 0 probability that we'll pick her second. So the first name chosen from the hat and the second name chosen from the hat, those are not independent of each other. So we have independent events when they have no influence on each other, but they're not independent if one of them affects the other, such as picking names out of a hat, or if we're picking cards out of a deck. If we pick a card and then keep it out of the deck, that will change the probability of what's left because now there are only 51 cards in our deck. So if we want to talk about the probability of two independent events happening, then we say that's the probability of A and B. And we talked about this last time a little bit, and we see that it's the product of those probabilities. So as long as A and B are independent, then calculating these probabilities is just multiplying those. So rolling two dice, if we want to look at the probability of both of them being 1, well, there's a 1 in 6 chance for the first one and a 1 in 6 chance for the second. So the product gives us a 1 in 36 probability. If we roll two dice and we want to know the probability of, one of them being a 1 or the other, this is what we were looking at last time. So we can add them together, the probability that we get the first one a 1. So that's our 1/6. The probability the second one's a 1 is also 1 in 6, but we have to subtract off the overlap. So that 1 in 36 chance that they're both 1s. So we get an 11 in 36 chance that if we roll two dice, then one or the other or both will be 1. If we're looking at probabilities and we have two events occurring and they are not independent, then what we have is something we call conditional probabilities. So here, if we talk about A and B having an effect on each other, we can think about doing B first and then A. So if we're talking about the probability that A occurs, we're going to have a probability that A occurs given that B has already occurred. So we call this the conditional probability of A given B. And we use this notation where we write P and then we have A and a line B. And again, we read that out loud as the probability of A given B. So we're really looking at the probability that A happens given that event B has already happened. If we have two events that are not independent, then when we're looking at the probability of one of them happening, it's really affected by the other one. So if we think about doing these in order and we say that event B has already happened, and then we want to know what the probability that A is going to happen as well, we can say that we're looking for the probability that event A occurs given that event B has already occurred. We call this the conditional probability of A given B, and we write this with our probability notation where we put this line in between A and B. So let's consider this example we were talking about before. We've got three names in a hat, Ollie, Brandy, and Cruz. So let me draw a big old top hat here. And we've got like 3 slips of paper one with Ollie, one with Brandy, and one with Cruz on it. And we want to look at the probability of not choosing Brandy second, given that she was not chosen first. So as we look at this, if Brandy wasn't chosen first, then we have two choices for who was chosen first. So if it wasn't Brandy, then we're either looking at Ollie having been chosen first or Cruz having been chosen first. So if we've taken one of these out, let's say we've taken Ollie out, so we're just left with Brandy and Cruz, then in this case, there is a 1 in 2 chance that we're choosing Brandy second. Or there's also a 1 in 2 chance that we're not choosing Brandy second and that we're choosing Cruz. So after first choosing Ollie, if now we choose Cruz, that's a 1 in 2 chance. Similarly, if we look here and say, okay, instead of choosing Ollie first, if we had chosen Cruz first, so we're just left with Ollie and Brandy as options for second, then not choosing Brandy in this case would mean that we chose Ollie second. And we can see that since there's just these two names in here, there's a 1 in 2 chance that we've chosen Ollie second. So in both cases, so no matter what happens the first time, if Brandy's not chosen, then we're either in the first case here or the second case. And if we're in the first case, there's a 1 in 2 probability that Brandy is not chosen. And if we're in the second case, there's also a 1 in 2 probability that Brandy is not chosen. So we end up with a 0.5 probability that Brandy is not chosen second, given that she's not chosen first. No matter which way we do this, which case we're in, the probability of not choosing Brandy second, given that she wasn't chosen first, is 1 out of 2. Another way of thinking about these probabilities now is that if they're not independent, if we want the probability that A and B both happen, we're still going to get a product. Remember, if these were independent, we said that the probability of A and B was just the probability of A times the probability that B happens. So when they're independent, we just took the product. Here, where they're dependent, then we need to actually multiply not just the probability that A happens, but now we have to multiply it by the probability of B happening, given that A already happened. So now we can think about having our names in the hat and looking at what is the probability that she is not chosen first or second. So we were just calculating, we saw that the probability that she is, our conditional probability here, that Brandy is not second, given that she wasn't first, we just calculated that one to be 1/2. And the probability that she is not first, well, there are two options. So if we have 3 names in a hat, there's a 1 in 3 chance that she's chosen first, which means there's a 2 in 3 chance that she's not first. So the probability that she is chosen neither first nor second is going to be this product, which is 1/3. This totally should make sense, because if we think about this, if we're picking 2 names out of the hat, there's going to be 1 left. So the probability that that last one is Brandy is 1 in 3, because it could be Ollie, it could be Brandy, or it could be Cruz. So we can think about this a couple of ways, but using our conditional probability formula, we can see we end up with a 1 in 3 chance here just by taking the product. So Again, if these were independent, we would have the similar formula, but we would have the probability of A and B would be the probability of A times the probability of B. And now, if they're not independent, we see that instead of multiplying by the probability of B, we have to say the probability of B given that A has already happened.